Swayam Prabha. Digital India. Educated India.
Welcome to another lecture on control systems. So we'll continue with what we were discussing in the previous lecture, which was certain refinements of the root locus. To be precise, we ended the previous lecture on this note that we looked at this angle of arrival and departure from complex poles and zeros, and we saw how we can evaluate that. Actually, I told you that I'll probably postpone the formula for that angle of arrival or departure till this lecture, but it turned out that I eventually ended up giving the formula in the previous lecture itself. So in this lecture, probably what I would do is I'll actually take an example and solve, okay, and I'll probably not take an example with numbers, but a very general sort of an example with symbols, and we'll still see this angle of arrival and departure does give us very valuable insight, okay, and it will hopefully reveal to you the power of this root locus based analysis, which is a graphical tool, okay. So consider this transfer function. Let's call this first transfer function as G1s, which is s plus epsilon whole squared plus d2 squared upon s squared into s plus epsilon whole squared plus d1 squared, okay. And consider another transfer function which is almost of the same form, and you would be even tempted to believing that the root locus and everything would almost be the same for these two transfer functions. But we'll see there's something very interesting that happens, yeah, and that conclusion about that can only be drawn by simply looking at the root locus. So let's say that d2 is greater than d1 and epsilon is a very small positive real number. Okay, fair enough. We're not giving any numerical values here. We're just saying that d2 is greater than d1. That's all we are saying. So let's look at the pole zero map for the first system. Okay, we obviously have a pair of repeated poles, yeah, at the origin, and then we have a pair of complex conjugate poles like so. So since it's epsilon distance away, these are, the root is at minus epsilon plus minus jd1. So epsilon is very small, so it's almost sticking to the imaginary axis, but not quite. There's a small epsilon difference between the imaginary axis and the pole. Okay, that's a small distance. So that's where another pole is. So another pole is, and since d1 is d1 is less than d2, therefore the complex conjugate zeros will be above these two fellows. Okay, side by side, let me draw. So this is for g1. Side by side, let me also draw this for g2. Okay, so this is r, this is jr. So see, everything remains the same as it is, except for the fact that these complex conjugate poles and zeros have interchanged positions. Now you might wonder, after all, what difference can it make? See, one thing you see at any point on the real axis, in either case, there is always an even number of poles plus zeros to the right. So there is no point on the real axis other than this degenerate point, other than this origin, of course at the origin the root locus exists only for k is equal to 0, but for any positive value of k, yeah, you do not have any point on the real axis qualify as a point on the root locus. What is the other important observation? The other important observation is that there is going to be the difference between the number of poles and zeros is 2, so there is going to be 2 asymptotes. Obviously if there are 2 asymptotes, they will have to be along pi by 2 and 3 pi by 2, okay. What about the location of the centroid of those asymptotes? Well, it turns out actually for complex poles and zeros, it is only the real part of the pole and zero that contributes towards the centroid. So where is the centroid? You can as well guess that the centroid is, because this is 0 plus 0, so the pole 0 plus 0 plus minus epsilon plus minus epsilon minus, what is the real part of this? This is minus epsilon minus epsilon. Yeah, if you want to write this as then plus JD minus JD, they will cancel out. Plus JD1 minus JD1 will cancel out here, and plus JD2 minus JD2 will cancel out from the other, or rather D2 will cancel out here and D1s will cancel out here. So anyway, the epsilon also cancels out here, and this is divided by 2. So this is going to be 0. So in both these systems thus far, we have seen that there is nothing to choose from. Yeah, so it might seem like we are splitting hairs here. I mean, we are just unnecessarily making this too complicated. There is basically hardly any difference between these two systems. After all, they are both only epsilon distance away from the imaginary axis. They are so similar in every aspect, other than this one crucial aspect which we are now going to investigate, which is the angle of arrival and departure at those complex conjugate poles and zeros. So as I said, I do not need to investigate them at all 4 points. I am just going to investigate, say in this case, the angle of departure from this pole and the angle of arrival at this 0, and likewise by symmetry argument I am going to just draw the root locus here, okay. So let me get started. Alrighty, so what have we got here? Let us see, if I am focusing on an epsilon ball around this, yeah, and I choose a point inside this as a valid point on the root locus for instance, and the angle is theta. So then applying the angle criteria, I get 2l plus 1 times pi is going to be equal to, notice the angles from the poles, the angles from the zeros rather. This will subtend an angle pi by 2, this will subtend an angle minus pi by 2, so it is 0. So it is pi by 2 minus pi by 2, that is the sum total of the angle contributions from the zeros. What is the angle contribution from this pole? See, a point close, as I said, argued earlier, no, this point is very close to this pole, so it is almost equal to pi by 2 itself. So it is minus, so this is summation theta z, that is going to be equal to 0 in this case, this is minus. So now I am counting from this pole, so it is pi by 2, okay. What else? See, there are 2 poles here, so I have to count twice, that is important. If I am counting for the angle from a repeated pole, then I have to count for the multiplicities. So what is this angle? This is some pi by 2 plus some alpha. Of course this alpha is going to be very small because the epsilon is small, I have already said that. So this is pi by 2, so this is pi by 2 plus alpha plus pi by 2 plus alpha, alright, fair enough. But that is not all. Now here comes in this theta, which is basically the angle of departure from this particular pole, right, that is the unknown to be determined, okay. This alpha is not an unknown by the way, this alpha is a very small angle, I am just calling it alpha, you can call it 2 degrees, 3 degrees, it will depend on this value of epsilon. Since I have not given any numerical values to these epsilons and these d's, this is basically tan inverse epsilon by let us say, what is this, epsilon by d1, yeah. So if you give some numerical value to epsilon and d, then you will get this alpha as tan inverse epsilon by d, that is all it is, okay. Now this is what I am going to solve for. So you see that the contribution from these two zeros is 0, so this goes to 0, because 1 0 is above, 1 0 is below, so this is minus pi by 2, this is pi by 2, so they add up to 0. What about the contributions from the poles? So this pole contributes pi by 2 this contributes pi by 2 plus alpha, and a repeat of it also contributes pi by 2 plus alpha. So what I then land up with is the following equation. I have this is 3 pi by 2 with a minus sign of course, minus 2 alpha plus theta is equal to 12 plus 1 pi. Okay. So I am going to go over to the next slide now, and let me write that down neatly. So 12 pi plus pi is equal to minus 3 pi by 2, minus 3 pi by 2 minus 2 alpha minus theta, right. It is the same equation as I have written here. Okay, I have probably put in a minus plus sign incorrectly. This theta is inside this bracket, so it should be a minus sign. Yeah, it is a minus sign. So this is minus theta. Okay. Now push in this 3 pi by 2 on this side. What I then get is pi plus 3 pi by 2. So it is 5 pi by 2. So 12 pi plus 5 pi by 2 plus 2 alpha is equal to minus theta. But what does that mean? Indeed, if you now look at this, yeah, what does it tell me? This I can clearly discard, because this is just going to give me, you know, a multiple of 2 pi rotations. Yeah, so this does not really matter. What about this? This is 5 pi by 2. What is 5 pi by 2? It means 5 quadrants. So you rotate along 4 quadrants, you come back where you were. So I can actually write this as, you know, 4 pi by 2, that is 2 pi. So that is again 12 plus 1 pi plus pi by 2 plus 2 alpha is equal to minus theta. So have I made a mistake here? It is 4 pi, so that is 2 pi. 2 pi. So this is L plus 1, I am sorry. This is L plus 1. L plus 1 into 2 pi. Yeah, 2 times L plus 1 pi. So this is basically not going to count. So all that it matters now is, therefore, theta is equal to minus pi by 2 minus 2 alpha, and remember alpha is a very small angle. Yeah. Okay. So what am I going to deduce here from this? Let me just see this. Okay. Okay, I think I should actually consider a single pole here, probably. Yeah, to make this more drastic. Yeah, I should just consider a single pole at the origin, maybe not a double pole. Okay, sorry about that, but in the process, hopefully you have learned what happens if a double pole is there. But yeah, this is not going to be that interesting, so I am just going to make things interesting. So I am going to make this a single pole. So all of this calculation here, you see, I am going to just ignore this another pi by 2 plus alpha. Okay. So there is nothing wrong with this, by the way. Whatever I have done so far, the calculations are correct, everything is correct, only that it does not make it as interesting as I thought it would. So I am going to just change things around a bit. Yeah, that is the only reason, there is nothing. So whatever if you followed the lecture up until now, you have not missed anything, or you have not lost out on anything, but it is just that I do not find this very interesting. So I am just going to sort of go ahead and consider the other case. But the good thing is that now you have learned that if there are multiplicities of roots, then also you consider them counting for the multiplicities. Okay. So hopefully that is a lesson. But to make things more interesting, here is what I am going to consider. So now look at this expression here. Okay. So this is a rough calculation here. So what is this? This is basically telling me that 12 plus 1 pi is going to be equal to minus pi minus alpha minus theta. So let me now go to the next slide. So what that means is, it is going to tell me that 12 plus 2 pi is equal to, so I am just pushing this pi on the other side, is equal to minus theta minus alpha, correct? Yeah. Yeah, I suppose that should be correct. Yeah. Now I hope I am not making a mistake here. Yeah. Now hopefully there is no room for any error. Yeah. So it's, let's say, yeah, I think it should be right. Okay. Yeah. So now you see, if I push this in, this is going to be nothing but 2 pi taken L plus 1 times common, and this is going to be equal to minus of this is going to be equal to theta plus alpha. But this is obviously, whether you go 2 pi times clockwise or anti-clockwise, the negative sign just implies you go anti-clockwise. So what this basically means is that theta is going to be minus alpha. What is minus alpha? So if this is your reference datum, then minus alpha is basically this direction, no? This is minus alpha. So it basically means that from here, if you start like this fellow is going to emerge in this direction, okay, and therefore its counterpart here will emerge in this direction like this. So if you are keeping this very close to the imaginary axis, you can immediately see that as you start increasing your values of gain k, almost immediately it will cross over to the right half plane. Yeah. And now you apply the same principle around this 0 here, apply around this 0 here, okay. If you apply it around this 0 here, what is the angle of arrival and departure? Let us account for the angles. So again this is going to be some pi plus beta, where beta is a very small angle given by tan inverse epsilon by d2, yeah, tan inverse epsilon by d2, so that is going to be beta, right, very small angle, right. Now this is going to be just beta, and since now there is no more repeated multiplicity, so it is going to be coming only once, okay. What about this? The angle contribution from this is going to be pi by 2, but that is going to be cancelled out with the angle contribution from this, which is also pi by 2. So this pole and 0 effect is nullified. So the only effect that you see here is this pi by 2, right. So for the arrival angle at the 0, we have the angle contribution from this pole, which is pi by 2. So the angle contribution from the zeros themselves are theta plus pi by 2 minus the angle contribution from this pole is pi by 2, as I said it will cancel out, but I am still writing it for the sake of completeness, pi by 2, and from this pole is going to be another pi by 2 plus pi by 2, and from the origin it is going to be pi by 2 plus beta. Yeah, this is going to be some 2l plus 1, some odd multiple of pi, alright. So what does this give me? This gives me that theta plus pi by 2 minus pi minus beta is equal to 2l plus 1 pi. So that gives me theta is equal to, of course, okay, this pi by 2 will cancel out already, so I am not going to write this again. 1 pi by 2 is cancelled out from 1 pi by 2 here, and you have just pi remaining here, so minus pi. So theta is going to be equal to 2l plus 2 pi plus beta, which is going to be well, 2 pi you extract out of here, so that is just a multiple of 2 pi. Again, whether you go clockwise or anti-clockwise does not matter, this is just beta. Yeah. So this theta is going to be equal to beta, it turns out. What does that mean? If it is beta, then if this is my reference datum, then this is my beta. Yeah, so this is going to be my angle of arrival at that 0. So this fellow will arrive at the angle at the 0 in this fashion with an angle beta, making an angle beta here, just like this fellow left with an angle minus alpha here. So basically I can then roughly sketch this like this, and in the same fashion sketch this like this. Now I leave it to you as an exercise to check But if you apply similar arguments here, you will see that unlike in this case, here just flipping the positions of this alpha and the pole and the 0, you will get a plot that looks like this. In other words, you immediately see the qualitative difference here. Yeah. So of course, the other thing that needs to change here is this will have all its branches along this. Yeah. So there will be no asymptote like the one I drew in the earlier case. That was because we were considering this repeated poles at the origin, but now we are no longer considering that. Yeah. Yeah. So that kind of completes the picture. All right. So that is the root locus. Let me draw this with a red line here. This is the root locus for this, and I leave it to you as an exercise to check by the same method that I have employed for this, that in this case when you have flipped the position of the pole and the 0, when the pole is above the 0, then no matter what value of k you choose, your closed loop poles are always going to be stable. Okay. So you see, just by applying this angle of arrival and departure, you can conclude so much about systems like these. Okay. So there are special systems, some particular systems where knowing about these refinements help you to infer quite a lot. Okay, that was basically the point I was trying to make. Now, if you permit me, if you indulge me a little, I would want to go back to this example we discussed in the previous class, and I would say that there is a connection with this angle of arrival and departure, and that connection can be established through something called continuation of root locus. Okay. So how is this relevant, you might wonder. Now, if you recall the system we had considered in the previous lecture, we had it s square by s plus 9, the one that I called as the most interesting case, the most interesting system, so to say, right. Okay. So let us quickly re-sketch that, because now that you know what it is like, yeah, so it was. So we had this repeated poles here, right, and we had this asymptote here, we had this other pole here, and we had a 0 in between somewhere here, that was a 0. All right. So now here is how the root locus sketch looked, right. Yeah, I am not sure if my drawing abilities or limitations will permit me to make it symmetric, but yeah, I am reasonably satisfied with the kind of symmetry I have managed to capture here. Okay, yeah, so there it goes here and here. Okay, so you see here, you had this 3 branches approaching here and 3 branches leaving here, all right. Now one might ask, in the same fashion like we have drawn these angles of arrival and departure here, you see when there are 2 branches colliding on the real axis, yeah, either after collision they go along the real axis in case of a break-in point, or before collision they were along the real axis if it was a breakaway point, and after collision they will always emerge at right angles. Why am I saying they will always emerge at right angles? Yeah, here is where this angle criteria and this idea of this arrival and departure angle makes sense. Now you might wonder, why are we talking about arrival angles and departure angles at a break-in point? After all, we have said that arrival angles and departure angles only make sense for complex conjugate poles and zeros, but there are no complex conjugate poles and zeros here. Now that is quite true, but you see there is this notion of so-called continuation of root locus. How so? So what are we actually sketching here? If I may draw your attention back to what we are doing here, here is what we are sketching. This is the plant we have in a unity feedback configuration, and we are basically varying this k, and we are sketching the locus of the closed loop poles. Now what if I put this k is equal to k1 plus k2, okay. So instead of considering this as a single parameter, there are say 2 knobs. So k is basically like a tuning of a knob. So let us say I have 2 knobs. So let us say K1 allows me to vary the knob between 0 to say 500, and K2 allows me to vary the knob from 500 to whatever desired value, let us say 5 into 10 to the power 20, whatever value I like. So then initially I would have K2 set to 0, I would not invoke K2, K2 would be off, alright. I am just going to turn this knob K1, alright. So if I am continuously changing K1, what is essentially happening? What is happening is that I am going to keep changing K1, and at some point, the roots, so you consider K1 s plus 1 s squared by s plus 9 plus 1, So you consider this to be your nominal equation, okay. So you consider this to be your nominal equation, right. In other words, your nominal equation then is s squared times s plus 9 plus K1 times s plus 1. So you put in this K1 is equal to 500 at its upper limit, okay, and you consider this now to be your nominal closed loop, so this to be your nominal open loop poles given by the solutions of this equation, okay. In other words, in the language of the root locus, what is happening is, I am saying that originally my open loop system's poles were here, but as I have varied it all the way to 500, suppose this branch has come here, and this branch has obviously then come here, and this branch has come here. So now, if I am just interested in how the roots vary or how the closed loop poles vary as K2 is varied from 0, so the K2 0 setting is actually the 500 setting of K1, but I am only interested in when K2 is turned on from that instant onwards, alright. So then for me, who is interested in studying the variation of K2, I might as well, instead of treating this original plant, I might as well treat this, wherever the closed loop poles are for K1 at its maximum value, that is 500, that might be the starting point for me at K2 is equal to 0. So then I will treat this as my nominal open loop poles given by the roots of this equation, and then I will continue to sketch the plot from there onwards, okay. So that is the continuation of the root locus, okay. So I split it up into two terms, I ramp up one term to its highest possible value while keeping the other term off, and then I see where the roots have migrated, alright, and then I call them to be my now nominal system. Only when K2 starts to be effective, from that point onwards, that is my nominal system, okay. So by the same token, where am I getting with this, now you might ask. So by the same token now, once again, let me draw this locus. By the same token, you originally start with this and this, and then suppose you varied this K1 term till you have arrived at this break-in point, okay, till you have arrived at this break-in point here, okay, and at that point, now you will see where has this branch come in, this branch has now come in here. So now at this point, let us say at the K is equal to K dash where the break-in happens, the maxima is so called maxima or minima or whatever is attained, in this case neither, because it is both a break-in and a breakaway. So now I redraw the modified locus now. So for me now, no longer are these points my open loop poles. The open loop 0 of course remains still the same, but now I have a triplet of, so this if I remember was -3 and this was -1, so now I have 3 poles here. So now I am going to study how this behaves, that is going to be from K dashed onwards. So I am going to continue, it is as if nothing had been changed, okay, I am just going to start off from where I left off, just like I do with these lectures often, right. So it is as if I am allowed to continue with this root locus beyond this point, as if everything that had been carried away in its history I can forget about now. So given that that is the situation, now you see there is a root locus segment in this portion, obviously, because there is only one 0 to the right, but beyond this the total number is 4, so there is no root locus. So then it stands to reason that there must be some breakaway and break in. If I want to find out this breakaway and how it goes, I can again apply this epsilon approximation and I can try to figure out which directions they will be breaking away. How so? So draw this epsilon ball around this. So since there are 3 poles here, so the angle made by this phasor is pi. So I have the angle with the 0, so summation theta zi is equal to pi, summation theta pi is equal to some unknown theta, let us say, so theta plus theta plus theta, because the angle of departure from this is going to give me the direction along which it breaks away, yeah. So now it is going to be 3 theta, alright. So now applying the angle criteria I get pi minus 3 theta is equal to 2l plus 1 pi. So therefore I get minus 3 theta is equal to 2l pi, or theta is equal to 2l pi by 3, okay. So what is that going to give me? That is going to give me basically that, of course, I know that one direction of departure is this, so that is for L is equal to 0, it is a 0 degree. For L is equal to 1, it is 2 pi by 3, so that is 180 degree or 120 degree, sorry. So this is one direction. For L is equal to 2, this is 4 pi by 3, so this, okay. So now you notice, now you cast your attention back here. So now I am allowed to continue this, so it is going to go in this direction, this is going to go in this direction, and this is going to go in this direction, yeah. So that is going to be my angle of departure from this point onwards, alright. Now using the same argument, you can now verify the claim I made a while back, that if this point corresponded to the intersection of, if a point, a breakaway point or a break-in point corresponds to the intersection of 2 branches of the root locus, like so. So suppose this is a breakaway point, yeah. So now you approximate this through the continuation of principle of the root locus as if I am looking at it as a point of multiple roots here, yeah. And because this is a point on the root locus, by virtue of it, it is always going to have, yeah, it is always going to be a valid point on the root locus, and therefore now if I want to find out in which direction it leaves, okay, all that I need to do is, again you see the same thing happens here. So the summation of the zeros is here 0, so 0 minus 2 theta in this case, yeah, is equal to 2l plus 1 pi, alright. So in this case it is 2l plus 1 pi. So if you just take it in this fashion, it will be like theta is equal to, of course you divide by 2, so it is L pi plus pi by 2, of course with a minus sign ahead of each of them, but really that does not matter, because you put L is equal to 0, this is minus pi by 2, you put L is equal to 1, that is minus pi by 2, that is minus 3 pi by 2, which is again plus pi by 2, right. So you can deduce that at this breakaway point which corresponds to the collision of 2 branches on the real axis, the branches will always break away at a perpendicular direction, okay. So this idea of angle of arrival and departure in combination with the idea of this continuation of this root locus allows us to infer that if there are a certain number of branches colliding at a particular point on the real axis, then they will break away. So I am allowed to now generalize this idea, okay, and you can think about trying to prove this in general. So I am allowed to generalize this idea if a point on this real axis is basically an aggregation of 3 different branches of the root locus which collide, or let us say q different branches, or let me call it any other number, let us say b branches. So here is the general result: if b branches of the root locus collide at a point on the real axis, yeah, then they will leave or depart with a spacing of, you see the symmetry will do the rest of the job for me. So what is the spacing between them? Now notice, if this is 2 pi, this is 2 pi by b, okay. So this is going to be basically 2 pi by b, okay, between them. And now if you have, in case of these 2 roots, you consider, can they really leave at any other angle? If for instance they leave at any other angle, so if it for example tries to leave along this angle, then the other fellow must leave at this angle, but then that will violate the symmetry condition. So the only way they can validate, they can follow the symmetry condition and also be spaced at 2 pi by 2, which is pi angles. So this angle is pi, isn't it? So be separated by an angle of pi, that is 2 pi by b. So there are 2 branches colliding, so they must be separated, as they leave they must be separated by 2 pi by 2, which is pi angles, and they must also be symmetric about the real axis. So putting these 2 conditions together, we see that they must leave at a perpendicular direction. Now similarly here also, you see there is this 3 branches colliding here, and you immediately see here, right. So if they have to be symmetric, then this is the only way they have left, and of course not just symmetric but also the fact that this is a segment on the real axis. So therefore one direction is already known. So if one direction is known, then you just go about finding out the other directions by adding this 2 pi by 3, then 4 pi by 3, and so on and so forth, yeah. So this is the general condition. So this is an interesting thing, an idea that comes into the picture only once you have learned about breakaway and break-in points, about the so called angles of arrival and departure, because ultimately what we are applying here is angle of arrival and departure at the breakaway and break-in point, and also not to forget the idea of the continuation of the root locus. Now all of this is a long winded way to say that all of this derives its roots in the simple angle criteria. So we have come so far with this angle criteria that we have been able to refine a plot to infer so many things qualitatively even without any actual graphical plot, okay. So that is the beauty of this whole method. Okay, a word of caution here now. So you might be thinking that I have dropped this negative sign here willy-nilly to evaluate all of this, yeah. In general you should not be dropping this negative sign like that arbitrarily, okay. So in this case, for example, here in this arbitrary, in this expression here or in any other expression, it does make a difference whether you consider this negative sign or not. Here it does not make a difference for the simple reason that look, this L can take up both positive and negative integral values, right, as we have seen earlier, as we have discussed. So here whether you take this -3 and divide it by a -3 here or by a +3 here, it won't matter, because if you take this to be -1, if you take this 3 to be a -3 in other words, then also you see it's going to be minus 2 pi by 3, yeah, which is the same as 4 pi by 3, which is 2 into 2 pi by 3. So angles eventually turn out to be the same. So at this stage you might wonder why I dropped this negative sign here. Is it again my usual carelessness? No, it's not. In this case it turns out that this negative sign will not matter, but in general it will matter. So maybe it's not a good practice. I could have retained this negative sign here as well, right. A final point about the refinement still remains. So based on this particular plot you might feel, okay, this is great. We have been now able to infer if there is a j omega axis crossing here based on these plots, right. But shouldn't there be a systematic way to also infer for any arbitrary system whether there is a j omega axis crossing or not? and indeed there is. So the final question, the refinement question, you remember we started with a lot of questions. How can we determine whether the root loci cross over to the RHP from the LHP or vice versa? If you think about it a bit, we have already seen an answer to this, and the answer lies in the topic that we just studied prior to this root locus, which is the Routh-Hurwitz condition, the Routh criteria, that is the Routh tabulation. How so? So let's take this example, because an example really illustrates things much better than I could have possibly put it in words. So let's take this S plus 1, S plus 2 and S plus 3, and I put this block together with a K. So what I am trying to look at is this plus 1 is equal to 0, the roots of this. So in other words, what I am trying to look at is, what is this, S squared plus 2S, okay, plus 3S plus 2 times S plus 3 plus K is equal to 0, is what I am trying to evaluate. Let us check, S squared plus 3S plus 2, yeah. So what is the final expression? It is S cubed plus 3S squared plus 3S squared plus 9S plus 2S plus 6 plus K is equal to 0. So in other words, this equation is nothing but S cubed plus 6S squared plus 11S plus 6 plus K is equal to 0. Now notice, what did the Routh array give me? I just discussed one such example as a closing statement to Routh array as an application of it. Now suppose I want to find out what is the bound on this K for stability. I might eventually conclude that for all values of K it is going to be closed loop stable, but that aside, if I do manage to find a critical value of K at which this crossover happens, then at that critical value of K, if I plug it in here, yeah, if I plug in this K crit here, what is it going to tell me? It is going to also tell me what the closed loop poles are, the solution of that equation. So let me try that here, okay. So let us write the Routh array for this, S cubed, S squared, S to the 1, S to the 0. So again, first two rows are pretty trivial, straightforward, 6 and 6 plus K. Next row is going to be 66 minus 6, that is 60 minus K, 60 minus K by 6, I suppose, yeah, 60 minus K by 6, I hope I am not making a mistake, yeah, right, and finally we have 6 plus K. So if this has to remain stable, this is positive, then we need 60 minus K to be greater than 0 and 6 plus K to be greater than 0. From these two, putting together the pieces, we need K is less than 60 and K is greater than minus 6. But of course, we are not even interested in these negative values of K. Maybe in the next lecture or thereafter, we will see how we deal with something called the complementary root locus, which deals with positive feedback systems, in other words for negative values of K. Okay, but for now our interest is only positive values of K, so we can as well translate this to the equivalent condition that K should be, because we are interested in only the positive values of K. Remember, the actual bound is this, but we are simplifying it to here because we are not interested in negative values. Okay, right. So this is what the range of K is. Now I wonder what happens at K is equal to 60. Yeah. So at K is equal to 60, let me put it here. So it is going to be S cubed plus 6S squared plus 11S, 6S squared plus 11S plus 66. 66 is equal to 0. Of course, I do not need to solve for this cubic equation even if it looks very challenging, because I know what happens at K is equal to 60. What happens at K is equal to 60 is a row of all zeros, and if I get a row of all zeros, then the preceding row gives me that factor polynomial or the so called auxiliary polynomial. Yeah. So what is the auxiliary polynomial? The auxiliary polynomial is 6s squared plus 66 is equal to 0, and I know that the roots of this auxiliary polynomial are the same as, at least whatever is the root of this auxiliary polynomial is also a root of the original polynomial. So therefore, at k is equal to 60, it turns out that omega is equal to, or rather s is equal to j plus minus square root of 11. I wonder what this value is. What is the physical significance of this value? Well, it is nothing but it is telling me that if I keep changing k, keep increasing k all the way up until it goes to 60, then eventually, now I am going to make use of the knowledge of root locus here, and probably that will be a good place to stop today's lecture as well. So we will have this minus 1 here, minus 2 here, minus 3 here. So of course we know that the root locus segment will be here and the root locus segment will be here. So of course there has to be some breakaway and break-in point here, but at the moment let me not care about that breakaway break-in evaluation, it's too much of a trouble. So what I am going to do is I am instead going to evaluate the, because I am not interested in that, I am just interested in drawing of all this. So there is some breakaway break-in point here which you can evaluate using the methods we have already shown you. So of course here it is easy because the numerator is just 1 and the derivative of the numerator is going to be 0. So you just have to apply d dashed n is equal to n dashed d. So n dashed is 0, so it is just d dashed n. So it is basically the derivative of this. Yeah, you take the derivative of this and equate it to 0 and you get the solution, right. So it's, I am not going to solve that, it is going to be a quadratic equation. Okay. Anyway, so the point is, where is the centroid? The centroid is going to be somewhere here, minus 3, minus 2, minus 1, minus, of course there is no 0, so it is 0. So therefore this is the difference between the poles and the zeros, open loop poles and zeros is 3. So this is minus 2. So this, it turns out, is going to be the centroid. Okay. And what are the directions of the centroid? Of course I know one direction, so the other directions are going to be, yeah. So already look, the asymptotes itself, they themselves tell me that this, at some value of k, I am definitely going to cross over to the right half plane. But this is going to tell me even more. It is going to tell me that at exactly k is equal to 60, something like this possibly happens. Yeah, so I start with this k is equal to 0 here and k is equal to 0 here, and then I go along this, and exactly at k is equal to 60, I reach the imaginary axis. But not just that, I reach the imaginary axis exactly at the point minus j square root 11 and plus j square root 11. In other words, the closed loop poles at the critical point, that is the point of crossover from the left half to the right half plane, the closed loop poles, a pair of them, of course one of them goes in this leftwards in this direction. So I do not know how far it has gone, I can of course factor it out and evaluate it, I am not interested. I am only interested in the imaginary axis crossing. So there is indeed, as this route array suggests, an imaginary axis crossing. It happens at the value of k is equal to 60, and at that imaginary axis crossing, a pair of my poles, closed loop poles, will be at plus j root 11 and minus j root 11. Okay. In other words, it will have oscillatory response at this point. And I know the frequency of that oscillation as well. So if you give a step input to the closed loop system and you vary the k and keep the k exactly at 60 fixed, then you will get an oscillatory response. And I also know that the frequency of that oscillation, those sinusoids and cosinusoids, would be square root of 11. So that is all the information that this particular refinement is allowing me to draw from this calculation. Okay. So that is how the root locus is actually quite beautiful and quite revealing in so many different ways. So we have discussed all the refinements that we wanted to about the root locus. We have shown you how a basic sketch of the root locus can be done, and hopefully we will also be able to motivate those refinements and why those refinements were actually necessary to draw more inferences than can appear at first glance. Okay. The next thing we are going to just qualitatively see is a topic we have already studied earlier from a different perspective. So for example, if you have a second order underdamped system, for instance, alright. So a second order underdamped systems would have a typical second order underdamped system would have a pair of poles like this. Now we also talked about what happens if there is an additional pole or 0. So my claim is, and we will see immediately from the root locus it follows, that if you have an additional pole to the left here like this, yeah, it's bad for the system. So remember this blue fellow, this is basically coming from Gs is equal to omega n squared upon s squared plus 2 zeta omega n s plus omega n squared, okay. And this black fellow is another pole that is coming in at s plus p. So this is that point p, okay, or rather minus p, right. So now we want to see that if you put this entire system, okay, if you put this entire system in a closed loop configuration like this with a gain k, sitting ahead of it like so, alright. We want to understand how the root locus behaves, and not just that, the root locus will actually tell us, yeah, what effect this additional pole has on the stability, okay. So you notice very carefully here, yeah, what can you say about this? There are 3 poles, no zeros. What can we know about such systems? What can we infer about such systems? The difference between the open loop poles and zeros is 3. So there must be 3 asymptotes. Not just that, the 3 asymptotes must also look like this exactly in the preceding figure, which means that there is always going to be a crossing over from the left half plane to the right half plane. Notice that originally the open loop poles are all on the left half plane, but if you keep increasing this k, as you keep increasing this k, this root locus would eventually, so probably you will have some asymptote that emerges from somewhere, I do not know where it is, maybe this is the asymptote. Let me draw the asymptote with a different color. So probably you have some asymptote like this, yeah. So you will see that the actual root locus would probably look something like this. So even if it is good for this particular pole because it is moving it more to the left half plane, yeah, and therefore probably making your system's response faster, but remember for stability we just need one bad apple. So I do not care if this pole is moving more and more to the left, thereby giving me very good performance. What happens to this pair, the original pair that originally constituted the second order block in blue? This is getting closer and closer to the right half plane, and indeed at some point it will cross over to the right half plane, thereby violating the, or sort of jeopardizing the closed loop stability of the system, right. What does that tell me? That this additional pole here is the culprit. Why? If this pole weren't here, what would be the case? So suppose I am just talking about this pole not being here. So let me draw the asymptote with actually green, because I am going to draw the root locus of the system without the additional pole in blue. What do you know? There are only 2 poles for this blue part that I have written in blue. There are only 2 poles. So 2 asymptotes, and 2 asymptotes that go off at pi by 2 and 3 pi by 2. And what is the centroid? Of course the centroid is exactly this, you can just check. So normally look, if I had not added this additional pole here, this transfer function, this original second order block would have had a root locus that would look like this. So this would actually allow me to keep increasing the value of k without jeopardizing the closed loop stability. But the moment I have an additional pole here, yeah, this kind of makes it worse for me, okay. So the effect of a pole, an additional pole, is detrimental to closed loop stability, is what we can infer from this insofar as the second order system is concerned. Why are we concerned about the second order system? Because look, we have spent quite a lot of time in studying this second order system in great detail and saying that, you know, many systems can be approximated to a second order system, right. So that is why we are concerned about the effect of this additional pole and 0 on the stability in the closed loop configuration of this second order system. So now to close the story, let us consider the addition of a 0 to the same second order system, Okay, so again we have this, okay, so I denoted this in blue, so let me draw this in blue, and now let me have this, so it's basically like S plus Z times omega n squared upon S squared plus 2 zeta omega n S plus omega n squared. Okay, so now I have an additional 0. So let me see what is the effect of the 0 on this stability. Okay, so let me mark the 0 here, this additional 0. Once again, as before, we can conclude that in the absence of the 0, the root locus would have been like this. Yeah, so if you keep increasing k, the real part of the poles will not change, it's only the imaginary part that increases, thereby reducing the rise time. So the settling time remains unchanged. This is like the constant settling time locus, isn't it, or part thereof, right? But now if you've added this, this makes a difference. Why? Because now notice that there is only a branch of the root locus here. Earlier there was no branch of the root locus on the real axis, so now there is a branch of the root locus here. Sorry, not in that direction, my bad, it must approach the 0, okay. So there is a branch of this root locus here that approaches the 0, and because of this it will actually force, you see, now there is this question of centroid or this asymptote does not arise because n minus m is equal to 1. So now obviously this cannot come all the way from infinity, no, because one of them has to eventually go to infinity here, because the number of poles is greater than the number of zeros. So at some point in between there must be a break in that is happening. Please try to follow this argument. Once again, depending on this location of the 0, you can evaluate this. I am not really doing that, it is a qualitative sketch after all, so I am not doing this sort of, I am not being very accurate with the angle of arrival and departure, that is for you to check as a maybe an exercise. But the overall scheme, in the scheme of things, the point I am making is that you see there is one more pole than the number of open loop zeros, one more open loop pole than the number of open loop zeros. So this one branch must go to infinity, but here I know that in a vicinity of this additional 0, it must approach the 0 as k tends to infinity. So therefore in between somewhere this reversal must happen, so there is a break in that must occur, as indeed you will see if you actually apply that condition for computing the break in for this, right. You will see that there is a break in point beyond minus z. So this point is minus z, so you will see that a break in point occurs beyond minus z. Yeah, all of this can be deduced just qualitatively without even any computation. But what does this tell me? Quite the dual of what I had earlier concluded. You see, the moment you add an additional 0 to this second order transfer function, forget about what it does to the performance computation and all. Right now we are just talking about the stability behavior of the closed loop system. What do we know about the stability? It turns out it has a positive influence or a good influence on the stability. Why? Because it causes the original root locus, which would have stayed constant, yeah, whose real part would have stayed constant here, now it moves to the left. So in a nutshell what we are saying is that the addition of an additional pole to the second order system has a detrimental effect on the closed loop stability because it pushes the root locus to the right. But the addition of this additional 0 to the second order transfer function has a beneficial effect on the stability of the closed loop system because it sways the root locus more to the left as you keep increasing k. Not just that, you will see that you can keep increasing k now. So this actually forms the motivation behind compensation techniques of what we call PD control or PI control or lag compensation or lead compensation, which we shall shortly take up possibly in the next lecture. Before that, we will also study another thing which we are not yet ready to study. We will also study the effect of non-minimum phase 0. So here remember, this additional 0 we have spoken about is on the left half plane. What if we added the 0 on the right half plane? So why am I saying we are not yet ready to study that? In order to do that, we will have to actually have a very brief discussion on complementary root locus. So we will embark on this discussion on a complementary root locus in the next lecture, and we will see in continuation with this idea as to where or what the effect of an additional 0 on this second order prototype transfer function is, provided the 0 is on the right half of the complex plane. okay. So this and much more shall be discussed, and we will hopefully venture into controller design in the next lecture, yeah. So till then, take very good care, thank you all.